So this is the first problem of today's contest, and in this problem we are given that Monocarp is participating in a programming contest which features 26 problems named A to Z, and the problems are sorted by difficulty. So moreover, it's known that Monocarp can solve problems A in 1 minute, problem B in 2 minutes, and so on. So we are given a string, and it simply means that on the first minute, Monocarp was thinking about the first eighth problem. Then on the second minute, Monocarp was thinking about this Cth problem. Once Monocarp has solved that problem, it's possible that he might be thinking about that problem after he has solved it. So like here, after 1 minute, Monocarp would have solved this problem, but still he's thinking about that problem for next 3 minutes. So eventually we have to find how many problems Monocarp would have solved. So this is a very simple problem for each character from A to Z. Just count, like for A, just see if this character appears at least once. If it is appearing at least once, Monocarp would have solved this problem. Similarly for B, check how many times this character appears in your string S. So how I have implemented this. So this is my implementation. In this, I have first taken N and S as input. Then for each character from A to Z, I'm just adding 1 to my answer if the count of this character is more than X. X is initially 1, and each time I'm incrementing it by 1. Finally, I can print my answer. Is it clear? If there is any doubt, like you can write in the chat. So let's go to the next problem. So in this problem, we're given Monocarp is practicing for a big contest, and he plans to solve n problems to make sure he's prepared. Now, each of these problems have a difficulty level, and the first problem has a difficulty level of 1, the second problem has a difficulty level of 2, and so on until the nth problem, so which has a difficulty of n. Now Monocarp will choose some order in which he is going to solve n problems. Whenever he solves a problem which is more difficult than the last problem he solved, he gets excited because he feels that he's progressing, and he doesn't get excited when he solves the problem, like when he solves the first problem in his chosen order. So this is just an example, and we are given that like if this is the order, he'll get excited when he solves this problem and this problem, because before those problems, the difficulty of the previous problem solved was less. So we are given a value k, and we have to find a order for which, like if Monoka follows that order, then he will get exactly he will get excited exactly k times. So we need to just print n distinct integers from 1 to n in such order that he gets excited exactly k times. So this is also a very simple problem, but we can do. See, if we have k, what we can do, we can first print from 1, 2, 3, all the way up till k, and then we can print n minus 1. This is one of the ways to do so, up till k plus 1. So this is decreasing part, and this is increasing part. In this, you'll get exactly k positions. This is first, second, this will be k minus 1, and this will be k. So for these k places, he'll get excited, and for all the future places, he won't get excited. Is it clear? Like you don't have to start with 1. You can like if you have any other order in like for which it is guaranteed that it will always produce a right sequence, you can print that also. Is it clear? Yes, no? Okay. So let me show you the solution. So this is the solution. And in this, I've just taken n and k as input. Then I have printed all the numbers from 1 to k. And then I have printed from n to k plus 1 in reverse order. So going to the next problem, we have this quiz. So in this problem, Monocarp is playing a computer game, and in order to level up his character, he can complete quiz. There are n quests in this game, numbered from 1 to n, and Monocarp can complete quests according to the following rule. The first quest is always available for completion, and the ith quest is available for completion if all j less than I quests have been completed at least once. Now, Monocarp can complete the same quest multiple times, and for each completion, the character gets some amount of experience points. For the first completion, the ith quest, he gets AI experience points, and for each subsequent completion of the ith quest, he gets BI experience points. Now, Monocarp is a very busy person, and so he has free time to complete no more than k quests. And your task is to complete the maximum possible, like your task is to calculate the maximum possible total experience Monocarp can get if he can complete no more than k quests. So see, in this problem, what we can do, let's say these are the n quests. So we can only take this quest if we have already taken the previous quest, right? It's mentioned in the problem, I think. The ith quest is available for completion if all the quests such that j is less than I have been completed at least one. So we can take this only when all of these have been taken at least completed at least once. So what we can do, we can iterate from I is equals to 1 to all the way up till last, and for each this we'll add all of these. Let's say this is 4, right? Or let's say general I. Like actually we won't be going up till n, we'll go up till minimum of n or k, but let's come to this in a moment, why minimum of these. But at for any general I, what our answer will be, our value will be that we can get is sum of all these values, sum of all ai's from such that I is from 1 to I, like sum of all of these values. Okay, I is from, like, let's say this is x. So sum of all of these values. So the sum of these, and what will you add in this? Now, among, for all the remaining, like you have k minus I quests left, right? So for all of those, you will do exactly, you will pick exactly one of these and you will complete it again and again. And that one will be maximum of all of b x's between 1 to I. Now let me explain this. So out of all of these 4, let's say you have 1, 4, 2, 3. You have 1, you have 1, 2, 1, 4. So see, if you have decided that you'll go up till this point, like you'll complete only these 4 quests. So this thing you'll eventually get. Like there is no other way. But for this, you should take, like let's say you had 6, k was 6, you had 6 quests. So for the remaining 2 quests, 4 quests are gone. For the remaining 2 quests, you'll pick the maximum for which bi is maximum, that quest, and you'll complete it again and again. So let me give you an example, and like you will do this for everything from 1 to minimum of this thing. I will be minimum. Why minimum of this thing? See, you cannot go more than n because you don't have more than n quests. And you cannot go beyond k because after that point, you are like simply trying to do k plus 1 quest when you are allowed to do only k quests. So let me take an example. Like from test case, let's take this first test only. So in this, we have 4 quests and we have 7, like we have to do 7 quests. So for I is equals to 1, what is the sum? Sum is 4 and the maximum value of b is also like it's 1 only. So now for this point, your value will be 4 plus maximum into k. K is 7 minus 1, 1 is already done. So this gives you 4 plus 6, which is 10. Now for I is equal to 2, your sum will be 4 plus 3, 7. And max is still 1. So now it will be 7 plus, this will be maximum is 1 into 7 minus 2. You have already done 2 quests, you have already completed 2 quests, and 7 minus 2 is 5, 5 plus 7 is 12. Now for the next time, I is 3, sum will be 8, max is still 1. So we can do something like 7 plus 1 into 7 minus 3. This is 8. 8 plus 1. So this is also 12, I think, right? And for the last time, I is 4. Sum is 10. Max is still 1. So 10 plus 7 minus 4 into 1 is 13. So out of all of these, what is the maximum? The maximum value is 13. So 13 is our answer. Is it clear? So let me show you the solution. So this is the solution. I have taken A and B as input. This is my final answer. This is the sum, and this is the maximum value of B up till now. So simply add AI to your sum, take maximum, and your answer will be nothing but maximum of answer or value, that is sum plus maximum. This is simply long, okay? Don't worry about this. Into k minus I minus 1. Why k minus I minus 1? Because k is 0 indexed here. When I was explaining, I was assuming that to be 1 indexed. Any doubts? Okay, like let's go to the next problem. So in this problem, we are given that winter holidays are coming up and they are going to last for n days. Now, during the holidays, Monocarp want to try all of these activities exactly once with his friends. That is, go skiing, watch a movie in a cinema, and play board games. Now, Monocarp wants to know that Monocarp knows that on the ith day, exactly AI friends will join him for skiing, BAI friends will join him for a movie, and CI friends will join him for board games. Now, Monocarp also knows that he can try more than one activity in a single day. Thus, he asks for our help for him to choose three distinct days X, Y, and Z in such a way that the total number of friends to join him for the activities, that is AX plus BY plus CZ, is maximized. So see, we are given three arrays like this, and we have to choose some X index in this, Y index in this, Z index in this. X shouldn't be equals to Y, shouldn't be equals to, like, this shouldn't be equals to this shouldn't be equals to this, and this should also not be equals to X. So, and we have to maximize AX plus BY plus CZ. This is our array A, this is our array B, this is our array C. So first of all, let's forget about n. Like, let's suppose n was around 100. What was the brute force approach that we could have used? Anyone? If this was the same problem, like this is the exact problem, n is only up till 100, like the size of these arrays is only up till 100. What could have we done?
Like taken all the triplets.
Yes, we could have used three loops, and we could have like calculated for all three triplets for which x is not equals to y and y is not equals to z and x is also not equals to z. But for this problem, we just have to optimize this a little bit. So instead of having three loops, let's try to have one loop, and the other two loops we'll try to use maybe some logarithmic factor instead of having a O of n factor. So what we can do, we'll still iterate over array A. Okay. Now, when I'm at this place, the only constraints that I have is I shouldn't use these two values, right? So first of all, I'll try, this is my array B. This is my array B and this is my array C. So among all the possible values, I'll always try to pick the maximum value of array B. Now it's possible that it's this, but let's say I have removed this value and this value. Now among all the other values, I'll pick the maximum value, and let's say this is that value. This is my X. So this is now my Y. This is the maximum value among all the remaining values. And now either I can just remove this value also from C, but what I can do, instead just pick the maximum value. So it's possible like the value is here, but let's say the maximum value came here only. Then I'll have to remove this and pick the next maximum. Otherwise, simply pick the maximum value and take the sum of these three values. Now, how can we pick, or how can we remove a value? Like, what data structure comes to your mind? What data structure is best fit for this? We need to pick maximum, we need to remove, and we need to insert some value. So all of these operations can be done by set or multiset or priority queue, but don't use set. Like, we can use set also, by the way, because what we will be actually inserting, we won't be inserting just values, we'll be inserting a pair of values and index. Why? Because like I said, we need to remove at this place, like we need to remove these two indices values, right? So in a set, we'll insert this pair. So we can either use set, multi-set, priority queue, anything. So let me show you the implementation. So in this, I have used a multi-set. You can use a set also. So first, I have taken my array A, B, C as input. Then I have inserted in my multi-set these pairs bi, this value appears in array B at this position. This value appears ci at this position in array C, right? So I've made these two multiset. Then I'm iterating over my array A, and I'm erasing bi value because it was occurring at ith index, right? And I don't want to consider ith index right now for either of array B and array C. So I will remove those two values. Now this is just a very cumbersome way to do this, but like I have said, if the maximum value in array in both these B and C are occurring at the same position, you'll either have to remove from one, and like what I was doing here, the maximum was occurring here, right? So if the maximum was occurring, if the maximum both of them is occurring at the same place, like after you have removed these two indices, like once you decided that this is your X, so if you have removed these two, let's say the next maximum is occurring at the same indices for B and C. So first take this and take the next maximum, which is, let's say, here. Next time you take the second maximum from, let's say, here, and take this. So this is how you have to do, right? So I have done it in a single line, but that's why it's like looking like that. So let me explain this. So what I have done, I'm checking, like this is SS is nothing but the second value of the pair. So if the second value of both the maximums, like both the maximums in second array after removing these are occurring at the same index, then I have two options. Answer will be maximum of either this thing or this thing. So this thing is nothing but take the maximum from array B and take the second maximum from array C, take the second maximum from array B and maximum from array C. Otherwise, if they are not occurring at the same place, then just do this thing. Take the maximum of both of these. Is it clear? Okay, why I used LL, long int. You don't have to use long int. I just have a habit of writing it. Actually, I haven't used long int. Like maybe I removed it, but usually I use, and I haven't used for this problem. And if you're talking about any of the previous problems, like probably you wouldn't have required there also. It's just a habit. Any other doubts? Probably we can. Like I'm not. I don't have a that solution in my mind, DP solution, but there might be. But this is like a very straightforward. Like how can you optimize a n cube approach? So actually, when like let's iterate over only one array, and from other two, try to pick the maximum. Okay, why LL and integer together? See, like your template can be different than mine template. In my template, I have my LL is defined as simply long, and like it's completely on like your habit. Like I have a habit of writing LL int instead of just writing long. Any other doubts? Okay, so let's go to the next problem. So in this problem, we're given that, okay, this is the easy version, and we'll do one thing. We'll cover both even and E2 simultaneously. Like I'll just give you an idea of even, and we'll discuss E2 only. So in both of these problems, we are given that Alice and Bob are given marbles of n different colors by their parents, and Alice has received A1 marbles of color 1, A2 marbles of color 2, and AN marbles of color n. Now Bob has received B1 marbles of color 1, B2 marbles of color 2, and so on. So now, after some discussion, Alice and Bob came up with the following game. Players are going to take turns, and starting with allies, on their turn, a player chooses a color I such that both players have at least one marble of that color. Now, then the player di- discards one of their marbles of color I, and their opponent discards all marbles of color I. Now the game ends when there is no color I such that both players have at least one marble of that color. So the score of the game is the difference between the number of remaining marbles that allies has and the number of marbles that Bob has at the end of the game. So in other words, the score is A minus B, where A is the number of marbles left with allies and B is the number of marbles left with Bob at the end of the game. Now allies wants to maximize this score and Bob wants to minimize this. So we are asked, if both players play optimally, what is the final score? So in the easy version, n is only between 2 and 6, and there are 10 to the power 3 test cases. In the hard version, n is between 2 and 2 into 10 to the power 5, and the test cases are up till 10 to the power 4. So in easy version, we can just brute force. If you have 6, what you can do, you can try all the combinations. For every, for each of these, just brute force. Like by brute force, I mean you have these 4, right? So let's say first allies took this, or allies can take this, or allies can take this, or allies can take this in the first operation. Let's say currently she took this. Now it's Bob from here. So for Bob also, try all the possibilities. And like this, you can do, like when you are playing for allies, just make sure that you are playing for allies to have the maximum value of score, that is AI minus BA. And when you're playing for Bob, you'll also you'll have to minimize this. But how to do this when n is very large, that is up till 2 into 10 to the power 5. So like n up till 6, we can just brute force because the test cases are also low. But in this, the sum of n can go up till this thing. So in this, what we can do, see, let's take one test case only. Let's pick this thing. So see what is given to us, AI, BI. If let's say if Allies chooses this color marble, his number of marbles will decrease by 1. His marble will become AI minus 1. And Bob's marble will become 0. Otherwise, if he doesn't chooses this marble in his turns, let's say Bob chooses this, then Bob will have BI minus 1 and Allies is going to have 0. So now it's up to Allies that what does she want, whether she wants minus 1 AI minus 1 marbles with her, or Bob can have BI minus 1. Like what is the difference? Like either she'll have this much or Bob will have this much. So what is the A minus B? A minus B is nothing but AI. And since this is with Bob, so this is kind of negative for her, right? Like either she's getting this much or Bob is getting this much. So if Bob is getting this much, this is kind of negative, like this thing, right? So like what will be, like if let's say either she'll get 3 marbles or Bob will get 2 marbles. So what is the difference? What is like how much will this affect? This will have a 5 marble effect on her. Either she will get 3 or Bob will get 2. If Bob gets 2, she'll get a -2 contribution because of A minus B. Otherwise, she'll get +3 contribution. So what is the difference between these two? It's 5, right? Yes, no. So now what we can do, either she'll get this much or she'll lose this much. See, for every AIBI, if she takes the move, if she chooses that color in one of her moves, she'll get this much. Otherwise, if she doesn't chooses this color and Bob chooses it, Bob will get these many marbles, right? So what is the eventual difference between these two? If let's say this is 2 and this is 3. So if she chooses it, she'll get +2 marbles. Otherwise, Bob will get 3 marbles. So if Bob is getting 3 marbles, eventually this will get subtracted, right? Eventually this is going to get subtracted because it is A minus B. So you can assume that either she'll have a +2 or a -3. So what is the difference between these two? It is 5. So either she can end up having 5 plus 5 score high, like whatever her score is X, either she can have like of like 5 difference in the score, right? A 5 unit difference in the score. Now this is valid for each of these. So for each of these, the difference in the score will be simply A plus B if Elias chooses it. And same for Bob also. If Bob chooses this is the difference that he'll be able to bring to the score. Why? Because simply AI, if he chooses it, he gets BI -1 marbles. If Elias chooses it, so she gets AI -1 marbles. So again, you'll be able to see that because he has to minimize it, either he can be with these many marbles, or if he's not with these many marbles, Elias is with these many marbles. So again, the only question is you get all of these values, and for each of these i's, this is the difference that you can bring to the score after choosing this. Again, for this is the difference. So what should Elias choose? At each moment, Elias during her turn will try to choose the biggest maximum of these AI plus AI plus BI, and same thing is valid for Bob also. So just store these values in a, just make a pair of AI plus BI, comma I, sort these array or vector according to these values, and just iterate in decreasing order or non-increasing order. And for each of these i's, if it's Li's turn, add AI plus 1, otherwise subtract BI minus 1. And finally, you'll get your answer. Is it clear? Yes, no, anything. Yes. You don't add and subtract this value. You'll add, if it's Li's turn, so you'll add AI minus 1, and you otherwise if it's Bob's turn, you will subtract BI minus 1. So let me show you the implementation. So first take A and B as input. I have created a multiset. You can just create a vector and sort it also. In your multiset, like in my multiset, I've inserted AI plus BI and I. Then F is 1. So again, this is not required if you're using a simple iterating over the vector. So this is just for me to know that if F is 1, then it's Li's turn, otherwise it's Bob's turn. So while X is having some size, pick out the maximum value. This is the maximum value, and this is the index for which AI plus BI is maximum. If it's Li's turn, add AI minus 1 to your answer, erase this. Actually, this could have been done here. and you don't need to do this. So just add AI minus 1. Otherwise, if F is 0, that means it's Bob's turn. Just subtract BI minus 1. And this is just for making, if F was 1, make it 0. Otherwise, make it 1. So this is the solution. So going to the next problem, F. So in this, we are given that Bursoft is the biggest IT corporation in Berlin. There are N employees at Bursoft company. These employees are numbered from 1 to N. And the first employee is the head of the company. And we are given that he does not have any superiors. So every other employee I has exactly one direct superior PI, and employees X is considered to be superior of employer Y if one of the following condition holds. Employee X is the direct superior of employee Y, and employee X is the superior of the direct employee X is the superior of the direct superior of employee Y. So like this is the general, like if some node is ancestor of another node, then we'll say that it is superior. So the structure of Bursoft is organized in such a way that the head of the company is superior to every other employee. So a programming competition is going to be held on. 2 persons team should be created for this purpose. However, if one employee in a team is the superior of another, they are uncomfortable together. So teams of 2 people should be created so that no one is the superior of the other. So no employee can participate in more than one team. So our task is to calculate the maximum possible number of teams that can be formed. So this is how we are given input. So let me explain the problem statement first. So see, we are given that we have this kind of tree. Okay, and see, this node has ancestors these. So we need to pair up nodes, like these 2 nodes can be paired up because none of these 2 nodes, if we pair these 2 nodes, none of them is ancestor of another. We can pair these 2 also. Okay, but we cannot pair, let's say, we cannot pair this node and this node. Why? Because one of them is ancestor of another. So this is all what we given in the problem. How to do this? See, there are many ways to do this. One of the ways is that you just find the leaf nodes, try to pair them. Like right now it's 3, like right now it's 4. You can just pair all of them, all the leaf nodes. Okay, don't worry about like how you don't actually have to pair them. You don't have to find the order, but you will always be able to. Like if there are 4, you'll be able to form 2 teams. If there are 5, let's make 5. Then find seal. So not seal, floor. So for these nodes, you can again make 2 teams. One will be left, and for the remaining, again follow the same thing. But better way to do this is like after this, you'll reach a point like you cannot. Maybe you are left with this. So don't consider this node as your leaf node. Okay, here there is only one node. It cannot be paired with anything. Remove it. This cannot be paired with anything. Remove this. This cannot be paired with anything. Don't consider this as your your topmost root node as a leaf node. So other way to do this is see, just start iteration from here. go down, and what are all the possible nodes that you can pair this with? What are all the possible nodes that you can pair with this node with? You cannot pair this node with any of the ancestor nodes. You cannot pair this with any of the direct children nodes or the nodes which are in the subtree of this node. But you can pair this node with any other node which is not either in the subtree of this node or which is not an ancestor of this node. So we can count such kind of nodes. If the count of such kind of nodes is more than what? Like if such nodes are there which are are not in the subtree and which are not directly in the ancestor nodes. And also there is one more thing, what that these there are nodes and those nodes haven't been taken by some ancestor nodes. Like let me draw it. See, for this node, how many nodes are in the ancestor? 0. How many nodes are in the subtree? 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many nodes are there for which I can pair this with? 0. Then when I come to this point, how many nodes I can pair this node with? 2. Why? Because there are 2 nodes which are not in the subtree of this node and not in the ancestors path also. So I'll use one of these nodes. Basically, there are these 2 nodes. Okay, I have used, so I can pair this. I'm marking this all the nodes that can be paired. Then let's come to this node. Again, how many nodes are there which can be paired? Like there were 2 nodes, now there are 1 node. And basically these are the nodes which are not in the path which is from root to this node and are not in the subtree of this node. Then coming to this node, now there are 0 nodes, right? 0 nodes that are not in the path from root node to current node and not in the subtree, and also like there were 2 nodes but those have already been used, so this cannot be marked. Also same for this node, cannot be marked. For this again I get 2 more nodes which are not in the subtree and also in the path from root node to current node. There were totally 4 nodes but 2 have been used, 2 are left, so this can be taken. Similarly, you'll get you'll mark these also, and then you'll mark these also, like if you do complete. So 1, 2, 3, 4, 5, 6, 7 can be teamed up. So how many teams are actually possible? Just take floor of this. 7 divided by 2 is 3.5. You'll get 3. So for this, the answer is 3. And what are those teams? So these 2 can be paired, these 2 can be paired, these 2 can be paired maybe. Okay. Any doubt? Like I'll explain again one more time. For each node, just have a number for which all the nodes that are not in the path of root node to that node and not in the subtree, and all the nodes which are left, which are not taken by ancestor nodes. Like these 2 nodes had already taken these 2. That's why they can't be paired. Is it clear? Yes, no. Actually numbering these nodes won't make any difference. If you number these nodes, how will it make any difference? I haven't actually traversed, right? If I have these as my numbers, how will it have any effect? This is what you're talking about, right? Numbering the nodes by. Yes, no. Okay, yes. What is your doubt if these are the numbers? You can ask your doubt. I think some students have already dropped. So you can probably if you have doubt, you can unmute yourself and ask your doubt.
Okay, hello.
Yes, yes.
Node 2 is paired with how many nodes? How can we pair node 2?
Yes, yes. Yes. So you don't actually have to find the pairing. You just, like, at this point, I knew that there are two nodes which are not in the subtree of this node and are also not in the ancestor path. So there are two nodes. I don't have to actually pair. I just know that, okay, this can be paired. That's it. So either you can pair it with 9 or with 10. Doesn't matter. When I come to this, I'll know that there is one node left which is not paired and which is not in the ancestor path and not in the subtree. When I'll come to this node, I know that there are 0 nodes left which are not in the ancestor path and not in the subtree, which are not paired. So that's why these two cannot be paired.
But the node 10 is like 2 level below the head of the company, and
Yes.
node 2 is 1 level below the head of the company.
Yes.
So can
But,
we pair
okay.
these two?
Yes. That is what I have explained here. So you can pair this node and this node. It's completely fine. Like this is not supervisor of this node. Why? The supervisor, like, what are ancestor nodes for this node? All the nodes that appear on the path from root node to this node. So that is 1, 2, 3. These are ancestor nodes for this node, not this node. So we can pair these two. Is it okay?
Okay, thank you.
Any other doubt that anyone else is having? Like, if that would have been the case, that you can this was also not possible, then the problem would have been really simple. We could have only made teams of these people. So then you could have just calculated like in each level how many nodes are occurring and just done like count of,
Then DFS traversal would have
yes.
worked.
Then just count the number of nodes in each level and
DFS
do
traversal.
count divided by 2. So let me show you the implementation. Okay, this is the implementation. I have first taken like n as input, then I have created a tree. Then I have counted for each node how many nodes are occurring in the subtree of it. So this will be useful later. So this is my second DFS function. This is U is my node, H is the height of the node. Why I need this? Because I know how many nodes. Actually, I don't need this. I haven't used H anywhere. And X is the number of nodes which the current node can be paired with. So increase your answer, like these are the total number of nodes that can be paired. So increase your answer by 1 if X is more than 0. If X is more than 0, you'll also have to decrease X by 1. Why? Because one of the nodes have been used here. That is going to be paired with you. So it is no more longer available for pairing. Otherwise, just count how many nodes are in the subtree of current node. Like, just count this thing. See, if this is the tree, when I'm going from this node to this node, all these 3 nodes are valid for now pairing beyond this, like for all the nodes in this subtree, right? So what you can do, you can count the nodes in subtree of all of, like, complete this node also, and when you're going in either this direction or this direction, just subtract the subtree of these nodes, and the remaining amount or count of nodes that you'll get is the number of valid nodes that can be paired. So just count the total number of nodes in the children subtree, and when you're going to any of the children nodes, just add this thing. X is the number of nodes that you got from above that are valid for pairing, and total is the total number of nodes in the children subtree of current node U, and subtree of V is just subtract that nodes subtree nodes. Like, for this, let's say we are currently here. From here we got 3 nodes. This is our X is 3 here. 1 is used, so X becomes -1. X minus 1 is 2. Then in this there are 2 nodes in this subtree, and there are 4 nodes in this subtree. So 2 plus 4 total is 6. And when I went to this node, I will do total, that is 6 minus 2, and I'll get 4. So these 4 nodes are now added to x, which was 2. These are also now valid nodes for pairing. So this is what I've done. X plus total minus subtree of v. Finally, I'll get n my answer as the total number of nodes that can be paired, just divided by 2, and you'll get the number of teams. So going to the next problem. So in this problem, we are given that there are 2 light bulbs arranged in a row. Each light bulb has a color 1 to n, and exactly 2 light bulbs of each color are there. So initially all light bulbs are turned off, and you choose a set of light bulbs S that you initially turn on. After that, you can perform the following operations in any order, any number of times. Choose 2 light bulbs I and J of the same color, exactly one of which is on, and turn off the second one. Turn on the second one, not off. And either like you can do the second operation also, which is choose 3 light bulbs I, J, K, such that the light bulbs I and K are on, and they have the same color, and the jth bulb is between them, and we can turn on the jth bulb. So now we want to choose a set S of light bulbs that we will initially turn on in such a way that performing the described operations, we can ensure that the light bulbs are turned on. So we have to calculate 2 numbers. The first one is the minimum size of S, and the second one is the number of sets S of minimum size modulo this thing. So this is the easier version, and this is like very simple. Like we can just brute force. N in this is only up till 1000, and the sum of n square over all test cases doesn't exist 10 to the power 6. So we can use something like n square approach or n square log n also. Let me explain. See, why n square log n will also work, because n particularly doesn't exceed 1000 also in this easy version. So if we clearly look at this problem, if we have one here and one here, if this is turned on, we'll be able to turn on this one also using the first operation, right? And then everything in between here can also be turned on using the second operation, because this and this is turned on. Maybe let's say 2 was here, we can turn this on. 2 is here also, we can turn this on. Now using this thing, we can turn on, let's say 3 here. If let's say 3 was here and the last 3 is like the another 3 is here. So using this 3, we can turn this on also. So like this, we'll be able to, let's say, turn this 4 and 4 off. So like this, we can turn using the single one, we can turn each of these switches on. So how many ways are there to do this? See, first of all, using this one, and let's say there are 5 and 5 here. So first of all, finding the minimum size of the set. What is it? Using this one, I was able to turn everything up till this point, not beyond this point. So I have to choose this one, right? And for this, in order to turn this on, I had to choose this 5. And let's take a little bigger example. So after 5, when I turn this on, I'll be able to turn this on, nothing after this. Then again, I'll choose this 6. I'll be able to turn on this. Because of these 2, I'll be able to turn on this 7th. And from this 7th, I'll be able to turn this 7. So the minimum size is 1, 5, 6, which is 3. So everyone, like, will you be like, can you calculate how I got this 3? I simply iterated from this one, got to this point. Like, I'm trying to get to the maximum position till which I can go. From this one, I can go to this. Then from each of these, try to jump to the next. What is the last position of 2? It is this thing. What is the last position of 3? It is this thing. What is the last position of 4? It is this thing. So this is the farthest that I can go. Similarly, for 5, what is the farthest you can go? Only up till this. For 6, you can go up till this. For 7, you can go up till this. After this, nowhere. So this is the way. Like, let's see for 1 again. For 1, you can go up till here. Now for each of these, try to go forward. For 2, you can only go up till here. For 3, you can only go up till here. And for 4, you can go up till here. So the minimum size is 3. This is okay. Now how to find, like this can be actually done in O of n. Like probably you can also write this kind of solution. But now how to find number of ways? So for this, we have to look at these problems. Now these 3 parts individually, like 3 different problems. First of all, for this, let's consider this. For this part, we need to count how many positions we can choose. Like for each of these positions, we'll choose only one. Like I have just shown, using this one, we can turn on each of these bulbs in this part. Using this only this single bulb 5, we can turn each of these bulbs. Using this single bulb, we can choose, like turn on each of these bulbs. So we won't choose more than these bulbs, but we have to see whether it's possible. Instead of choosing one, what if I chose 2? What if I chose 3? So for each of these, I have to find, for each of these, if I chose these bulb, then would I have been able to turn each and every bulb in this? If yes, so I'll count such bulbs. Let's say I got 5. So for the first part, I have 5 options. For the second part, let's say I have 2 options. For the third part, let's say I have again 2 options. So the total number of sets that I can have is 5 into 2 into 2. Now how to get this number? So let's see. So 1 is valid. One we have already seen 1 is valid, like the first place. How is it valid? I'll show again. Minimum size was 3, and now we are getting the minimum number of ways. Okay, so 1 is valid because from here I can turn this on, then everything here will be turned on, and because of this I can turn on, because of this 3 I can turn on this, and because of this 4 I can turn on this 4. So everything can be turned on. So 1 is a valid, this first place 1 is valid. And similarly, you can see this is also valid. Why? Because if you turn this on, you can turn this on, and then the same thing goes on. Let's see this, whether this 2 is a valid or not. Using this 2, you can turn on this 2. So now 3 and 4 can be turned on. Using this 3, you can turn on this 3. So if this 3 is turned on, eventually you can turn this 4 and 1 also on. And using this one, you will be able to turn this one also on. So we'll see this 2 is also valid. Similarly, this 3 will also be valid because this 3 will make this 3 turn on. Then you can turn on this one, and once 1 is turned on, we have already seen everything can be turned on. About 4 also same, and 2 we have already seen. This 2 is valid, so this 2 will be also valid. So here we have 1 2 3 4 5 6 7 8 valid bulbs. Here we'll have 2, and here also you can directly, by seeing, we'll have all the 4 valid. So our number of ways for this example is 8 into 2 into 4. Now you might be under the impression that every bulb in the section, like once you have found these sections, every bulb in those sections will be a valid option for starting point. No, it's not true. Let's see an example. Let's say our orientation was like this. So if we turn this 2 on, we'll be able to turn this 2, and then everything in between can be turned on. So 4, everything is turned on. But let's say we started from this one, then we can turn this one, but there is no way to turn these 2 on. So in this scenario, if this was how the bulbs were arranged, we would have 2 valid options as starting point. So for this part, we have 2 valid bulbs. For this, it is 8 2 and 2, 8 2 and 4. So this is simply 64. 64 valid operations, and 3 is the size of the set. Is it clear? Yes, no? So now we'll come to the part how to calculate this. This is okay. So actually the calculation is very simple because we can brute force. We can just brute force and find it in n square log n, something like this. So we'll just completely iterate over this. And for each of these, just find if this is your starting point, can you cover the complete range or not? So how to do this? Just insert everything in your set. go in this range, remove one by one from your set. Why set? Because it's easier. Like don't, otherwise it will be NQ. So just find the lower bound of this left and remove everything. Then you have found 2. So again, this is the starting point, like one position for 2, and what is the next position for 2, this thing. We can pre-calculate these, like the 2 places at which 2 occur, and just remove everything between these 2 from your set. So while you are removing these, you'll encounter 3 and 4. Do the same thing for 3 and 4 also. So this is in n log n. We can, for each position, we can find what is the maximum, or like what is the range in which can be removed. If that range is equals to the complete range, that is this complete part, then the bulb in that position is valid. So this is how we'll calculate all the valid bulbs, and eventually we'll multiply for each partition, we'll multiply those valid number of bulbs. So let me show you the implementation. So I have, like, the solution is a little bit complicated, like, but the idea is simple. So initially I've created two of these vectors. The first one will give me the position of the left position of the color of the first bulb, and this will give me the second position. So I'm iterating over this, and simply if A is -1, then simply give it this position for CIth color bulb. Otherwise, give it to B. So X is my total, like the minimum size of set, and Y is the number of ways. So this is the first part, is to find the number of elements in my set. So just keep on going, like this is simple O of n log n, this part up till now. Like just while your set is having size, keep inserting the element in your set, and if the element is occurring for the first time, then insert it in your set, otherwise just remove it. And while your set is still having some elements, that means that you can turn on some more bulbs. While this is true, you'll get all the bulbs that can be turned on in this partition. Once there is no other bulb that can be turned on, that simply means that your partition has ended. So increase your X by 1 at that point. So now, like, I have made a copy of I initially. So this is the J, and finally my I will be pointing at the end of the partition. So up till from J to I have to check for each value what all are valid positions for starting. So for each of those, what I have done, I have inserted everything in my set, like I said, and this is the places that have to be removed. So what I have done, while I have something to be removed, find the left position and map right position. Now it's possible, like sometimes I might get these not correct. So like actually I'll get, because A was always having lesser and B was having maximum, but still I have done like this check, this is not required. So find the left position and right position of this color, and everything between that needs to be removed. So while the minimum has anything more than it, more than or equals to it, which is less than maximum, remove it and insert that position in your rem. Rem is nothing but later on everything which is in rem for those colors also will remove, do the same thing. Finally, if the set size is 0, then I'll increase my val by 1. So when will be my set size 0? When everything between this original like previous value of I, which is j, and now new value of I, that is the complete partition is removed. Then I can take this as my one of the starting points for my bulb to be turned on. Finally, I'll multiply my y with this val. For the current partition, how many valid bulbs are there? There is only one thing that I need to explain. You might be thinking, like for each color, for each colored bulb, I'm iterating from here to here, and everything that is in between, I'm inserting that in remove. And then I'm using that to iterate over. But it's possible that I can have this kind of orientation. Like I'll iterate from here to here, insert these in my remove, then later on I'll iterate from here to here and insert these back again. So isn't it like, again I'll get this colored bulb back in my set, and again I'll start iterating this. So won't it form a cycle and I'll get a TLE? So now you might think like my solution will get hacked, but no. Why? Because that's why I'm using set. I'm not inserting actually in my set. I'm just like, once I have iterated from here to here, although I'll insert this in my rem, but I won't insert any of these values back in my set. So when I'll be iterating next time, when I'll be removing like here to here, when I'll be going from here to here, this value simply won't be in my set. Like I'm never inserting anything back. Okay. So it won't form a cycle. I think there are like better ways to do this. And finally, what we can do, we can print x, that is the minimum size of the set, and y is the number of ways in which we can make set s. Is that clear?
Yes, kind of.
Okay. So that's it. And thanks for joining. Bye-bye.